Hi all. So I thought I'd do a second video just to sort of recuperate some of the time that we've missed this week. But the last video just basically covered Newton's three laws. So the first law is an object will remain in a state of rest or uniform motion unless it's acted on by an external force. So an example of this you could say would be Earth going around the Sun. Earth will continue to go around the Sun. The Sun and Earth are a system, but if there's some external force, like an asteroid, and it comes to Earth, it might knock us off our current trajectory, and then we'll accelerate. We'll change. Our motion will change as a result, but then that'll be an external force. Okay. Second law was one which I didn't talk too much about last time, but it's F equals ma. But then I said don't go with F equals ma anymore. It's not okay. Okay. F equals ma is like the GCSE simplified version. Acceleration we know is the change in velocity per unit time, or rate of change of velocity. So if you merge the two of those together, you end up getting this new formula, which is F equals delta mv over delta t, which is what we're going to focus on today. The third law was every action has an equal and opposite reaction. And we talked about the Earth. We said about what my weight, I'm being pulled down due to gravity. I've got my weight, that's the force going down, and I have got a reaction force pushing me back up. But actually Newton's laws, they come in pairs. So every action has an equal and opposite reaction. I'm being pulled down, something needs to be being pulled upwards or towards me. So what I left you with last time was saying that Earth gets pulled upwards. Okay. What I wanted to do for the next 5-10 minutes in this video is just talk about momentum. Okay, momentum and impulse if we get onto it. Okay, so momentum, you should have studied it at GCSE, but if you haven't or if you've forgotten, momentum is something which has a mass, and is also moving. So I always think about a car and a motorbike. If you have a car and a motorbike on the motorway, both going at 70 miles per hour, well, which one's more likely to have the larger momentum? Well, the car is more likely to have the larger momentum because it's likely to be heavier. Okay. Then if you think about two identical cars, let's say two Mini Coopers, apparently the old type used to weigh bang on 1 ton. So imagine you've got two of those on a motorway. One's going at 70 miles an hour and one's going at 50 miles an hour. Well, which one's got more momentum? The answer is the one with the larger speed or the larger velocity. So now we've got two properties which we can link together, which sort of go towards our understanding of momentum. Now, even if you don't know what momentum is, hopefully you sort of followed that and it sort of somehow made sense. Okay? And the equation for momentum is actually relatively quite straightforward. It's just momentum equals mass times by velocity. It's the product of mass times velocity, or mass and velocity. Okay? And we write that in different symbols. Momentum is given the letter P. I can't remember the reason for that, but I can't use M. M is for mass. So P is equal to mv. That's our formula. Okay, and now if we think about the units, pause the video for a second and see if you can determine what the units for momentum might be. Okay, the SI base units, if you like. The units of mass we're going to give kilograms, and the units for velocity are just meters per second. Okay, so if momentum is just the product of mass and velocity, well, we can just literally do the product of the two units. So momentum is kilograms. I'm here. Thanks, Siri. It's just kilograms. Momentum is just measured in kilograms meters per second. Okay, it hasn't got any specific units. All right. Now, momentum's it's a very important quantity in physics, and it's because it's very similar to energy to some extent. Energy is a conserved quantity. You can't create it, you can't destroy it. Well, it just so happens that momentum is the same thing. You can't create it, you can't destroy it. Momentum is always conserved. Always conserved. Okay? You can't create it, you can't destroy it. So that's often written as the conservation of momentum. Alright, so just have a little think about that for a second while I just move my phone so Siri doesn't go off again. Right, there's a reason I just got up and moved over there, and I'm hoping you sort of spotted it. I was stationary to start off with, and then I got up and moved over there, which meant I had a velocity. My mass didn't change, My mass is not changing each second if we ignore the fact that I'm using a little bit of energy. So how on earth did I just gain momentum? If I just gain momentum and I'm saying it's a conserved quantity, well, where did that momentum come from, or where did it go? And if you think back to Newton's laws, there's another law which sort of links to it. And it's every action has an equal and opposite reaction. So if I was to get up and go in that direction, well, I have to push against the floor. So the floor goes back that way, I go in that direction. So something is being forced to go that way while I go that way. So what is it that's being forced to go that way? Have a little think. Pause it if need be. But it's as absurd as what I said yesterday, and that's the fact that I'm being pulled down, something has to be being pulled up. Earth is being pulled up while I'm being pulled down. Okay, so if I'm going to go in that direction, I am pushing against the floor is going in that direction. Now, obviously the floor, my house, is not going to start moving in that direction. The house is concreted to Earth. The whole of Earth ends up going in that direction a little bit more. But it's a minute amount, okay? It's tiny. It's an absolutely tiny amount, but it does happen. And then what basically we'll do over the next couple of lessons is we'll do a bit of maths, sort of, to really appreciate that and understand it properly. All right? So that's momentum. Anything which has mass and velocity has momentum, okay? So if we're going to get back over to Newton's second law, this idea of F equals ma, well, let's just have a look at this formula. We've got F equals mv, but I've said it's now the change in mv over delta t. Well, mv is momentum, so therefore we can say that F is equal to the change in momentum per unit time. That is Newton's second law, okay, which is the same as the one below. So Newton's second law is written as the force is proportional excuse my handwriting, to the rate of change of momentum. Okay? And then it also actually links back to the first law as well. But there you have it. So that's second law. So basically, every action has an equal opposite reaction. So imagine you were, I don't know, on a spaceship in space. So I've chosen space because there's no external friction, really. So you're on a spaceship and you're just sat there, motionless, okay? You're in deep space, motionless, okay? Well, if something was to be fired at you, so I don't know, someone chucked a ball and it came towards you, hit the side of the aircraft, well, that ball is going to strike the side of the aircraft, create a force, an impact on the side of the aircraft. That means the aircraft gains some momentum. So, I haven't really got much room here, but if you're over here somewhere in your spacecraft and you've got this external force which comes in this way, it strikes the side of your spacecraft, right? Well, that usually means that the thing that collides with you slows down. So the blue bit halts, it slows down a little bit. So this is the before scenario. And then the after might be that the blue ball has just reflected and is moving backwards slowly. Let's say the length of the arrow is like represents velocity. Well, now your red spaceship might be moving in that direction a little bit. Okay? So you've been thrown off course. So you've been struck by an external force. So now suddenly we can factor in Newton's first law. An object remains in a state of rest, or beforehand it was rest, or uniform motion, unless it's acted on by an external force. Well, this blue object is striking into the side of it, creating a collision. That's the external force. Okay? Every action has an equal opposite reaction, so there's a collision, there's an impulse in that direction, striking the surface of the ball. Well, both of them will probably deform slightly, but there's some sort of repulsion between the two, an electrostatic repulsion, which basically makes one fling off from the other. Okay, so there are a pair of forces involved, but the crucial bit is now we can factor in Newton's second law as well. Newton's second law is force is proportional to the rate of change of momentum. And I didn't actually say this before, but it's written as proportional because if you just get rid of the equals and say that, or the constant of proportionality is just 1, okay? The force is proportional to the rate of change of momentum. It's equivalent to, is equal to the rate of change of momentum, okay? But now, if you know the velocity of the ball beforehand, Well, and you know the velocity of the ball after, you know that the momentum of that ball needs to be conserved. So if the ball has lost a certain amount of momentum, that momentum has gone into the red spaceship in this case. Okay, so suddenly you can figure out by observing the motion of an object during its collision, you can work out how much the other object is going to gain its momentum. I haven't explained that particularly well, but police use this, or crime scene investigators use this to determine how fast a car is moving before a collision. And I'll give you an example of that shortly. But there you go. So that's Newton's first, second, and third law in a bit more depth. All right. Right. What we're going to do now is we're just going to apply this idea of conservation of momentum to a couple of sort of problems, and I'm going to give you an equation which hopefully you've done at GCSE. But momentum is mass times velocity, fine. So basically we have two objects, right? Let's just say they're vehicles, square vehicles and all. And let's say they're both opposing each other in terms of their motion. So one's going in that direction, one's going in this direction. We'll give this one mass 1, this one mass 2. This one's also going to have a velocity 1, this one will have a velocity 2. Basically they're just completely different values. So algebraically we've got m1, m2, v1, v2. Okay? This is the before scenario. And then the after scenario is, I don't know, we can make up whatever we want right now. But we can say that they collide, they stick together. I don't know, there's some sort of like suction thing on the side and they're going to stick together and they're both going to go in one direction. So let's say that's the case. And the combined mass now is m1 plus m2 because they are now one object, let's just say, both moving in the same direction. We're going to say that they both start moving in this direction, v. In fact, actually it's probably better if I change this to u2 and u1, and then the after is v. It's just v. You could say it's v subscript 1 plus 2. It doesn't really matter. It's just the total velocity after. Okay. The reason I've changed this to u is because when we did SUVAT, or the equations of motion, u stood for the initial velocity, and then we've got this after final velocity. Okay, so that's what we're going to do. So momentum, we've got two objects before, and both of those objects have their own momentum. So we've got the momentum of object 1, and we've got to add that to the momentum of object 2. So literally, when you combine momentum, you literally just add them. And then after, we've got p, we'll just say it's p after. So basically, the rule is the momentum of the system before must equal the momentum of the system after. That's the conservation momentum, that's what it means. Okay? So the object 1, this is object 1, we're going to say, well, p1 is equal to m1 u1. P2 is m2 u2, right? And that's going to be equal to the mass of the combined system, which is m1 plus m2, it's just the same as before, times by the final velocity v. Okay, so that's it. That is an equation when you've got two objects where they've stuck together. Okay, now I wouldn't remember this equation. I just remember, if I was you, I'd remember how to do conservation of momentum. Because what we'll now do is we'll change the scenario where we'll have an object over here, and it's going to collide with this other object. This, in fact, we'll do the exact same scenario. So we've got u1, u2, m1, m2, and then afterwards they're going to have changed. In fact, I'll tell you what, let's change it. Let's say that the second object was stationary. So u2 equals 0. It's a stationary object, okay? Then afterwards we'll say that all the momentum, we'll just say that this one here is reversed slightly. So that's going to be v1, and this one's going to be going in that direction with v2. Nothing's lost, no bits of debris have come off any of the vehicles. We can ignore any of that. That would be pretty negligible usually anyway. So this is our before and after scenario, okay? A stationary object m2 and a moving object m1. Afterwards m1 recoils and comes back the way it came, and m2 goes in that direction. Okay, so that moves away. So we can say that p1 plus p2 must equal p1 plus p2, but this is p1 and p2 after, and this is p1 and p2 before. So then you can't just cancel, they're different. Okay, in fact I'm just going to do some sort of like dash just to represent that they are different values. Okay. So P1 is M1 u1, and that's plus m2 u2. But u is 0, so that just goes. Okay, and that's going to be equal to m1 v1 plus m2 v2. So now we've got another formula where we've got m1 u1 will equal m1 v1 plus m2 v2. Okay. But if we just said for a second that u was not 0, so if it was not 0, let's just kept it as u2, sorry, then this whole formula changes slightly, because now we'll have m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. So now we've got a different formula again, which is why I wouldn't go about remembering any of these equations. Just remember how to do it, remember the process. Okay, and it's just conservation of momentum. It's a conservation law. So this is where we get two objects sticking together, or we get some form of explosive event that happens down here. Okay, we'll do another one, which is just a static explosion. Okay, right. Just going back to this quickly. One thing I didn't say was that, and you might have questioned it. Well, what if? How do we factor in the fact that things change direction? Well, the answer to that is u is not a speed; it's a velocity. Okay, so if you've got this as the scenario up here, you've got u1 going to the right and you've got u2 going to the left. Well, you have to take a direction as being positive. So I typically take going right as being positive, going left as being negative. All right. So if that's the case, whatever value this is, let's just give them values for a second. Let's say this is moving at 12 meters per second. This is moving at, well, let's go for 12 meters per second as well. Well, I would say that this is really negative 12 meters per second. That then factors in the direction, because after all, velocity is a vector quantity. Okay. One thing I didn't say earlier as well is momentum. Is that a vector quantity or a scalar quantity? Well, it's got to be conserved. If it has to be conserved, then you've got the momentum of something going in that direction, the momentum of something going in this direction, and they come together. Well, the combined momentum results in no momentum after. So it's got to be a vector, because the momentum in that direction can cancel out the momentum in that direction. I hope that made sense. So yeah, so momentum is a vector quantity, measured in kilograms meters per second, and if you want to factor in velocity, you just put the negative. So if we come out down here, let's say we've got a problem where we want to find out what v2 is, or v1 is, sorry, let's go for v1. So, and we're going to pretend that u is 0, which means we'll factor in this black equation, the one in black. Well, how do we know if v1 actually comes and recoils? If we know what u1 and v2 is, right, or are, we know all the masses of both the objects. Well, we basically plug it into this equation, and if v1 comes out to be positive, positive being to the right under my rules, then if it's positive, then that means it's actually moving to the right. If it comes out as a negative answer, that means that we're moving to the left. Okay, that will become more clear when you start doing a couple of problem-solving questions. All right. Right, hey all. I'm a little bit irritated, I won't lie. I've actually done this video already, but I had the blooming microphone turned off. Anyway, right, last time, and then I can rest. So what we have covered already, we've had momentum, conservation momentum, where you've had two objects moving and they collide together and they move off as one. So two separate objects becoming one. We've had another scenario where you've got two objects moving and then they come and move off separately. So you've got two different momentums to start off with, two different momentums to end up with. You could also have two objects that come together or colliding into each other. So you've actually got a negative momentum in the before scenario. The point is, momentum is a vector quantity. I can't stress that enough. But the last scenario which we're just going to cover is explosions. Okay, which actually I think are probably a little bit, they sometimes sound a bit more exciting, but actually they're a bit more simple if anything. So if we think of something like a cannon, right, beforehand the cannon is on this little pivot, you've got the cannonball in the middle, and I have no idea what values to make up for these, but let's just say the mass of a cannonball, I don't know, let's go for about a kilogram. Okay, and the mass of the cannon itself, I have no idea, but I can imagine it being pretty heavy, and you know, 100 kilograms, but I'll make the number slightly more obscure. Let's go for 120 kilos. Okay. Now, in an explosion, we assume that both objects are stationary to start off with, so the initial speed of the ball and the initial speed of the cannon are both 0. Okay, that tells us that the momentum of the whole system beforehand is 0. Alright? So that's the before scenario. Okay. Now, after, why did I do that? The after scenario, we're going to say that this cannonball has been launched and it's moving in that sort of direction to the right, and we want to find out what's going to happen to the cannon itself. So we want to find out the final velocity of the cannon, and we'll say that the final velocity of the cannonball is something really, really quick. So 50 meters per second is what I thought of a second ago. I mean, that's pretty fast. That's probably about 110 miles per hour, something like that. I think that's pretty substantial for a kilogram size mass to be moving. But we want to find out what happens to the cannon itself. Now, if you're thinking right ahead to the end of this whole question, hopefully you realise that there's no momentum to start off with. So, if you suddenly have that explosion and you've got a momentum going to the right, you must have a momentum going to the left, because combined, the right, the positive, and the negative to the left must cancel to make 0. So basically what we're hoping is we'll do the calculation, we'll get a velocity for the cannon, and that should come out as negative. But we'll see. Alright? So we're just going to apply the same rules. We've got this idea of momentum before is equal to momentum after. So the momentum before is the mass of the ball before, or the mass of the ball is the same as the mass of the ball after. Okay, we're going to assume that there's no debris that comes off, there's no little shards that come off anywhere. Let's just make it so it's a nice straightforward question. So the mass of the ball before times the initial velocity of the ball plus the mass of the cannon times by the initial velocity of the cannon must be equal to the mass of the ball times the final velocity of the ball plus the mass of the cannon times the final velocity of the cannon. Okay? If you notice, UB and UC, they're both 0, so these bits here just cancel, we just don't care about them, because basically that means the momentum before is 0. And that's going to be equal to the mass of the ball before, sorry, the mass of the ball, 1, times by the velocity of the ball after, so we're saying that's 50. That's our made up value, and it's to the right, so we're saying that's a positive 50. And that must be plus the mass of the cannon, 120, times by the velocity of the cannon, which we don't know what that is yet, so we're just going to leave it as VC. Okay? So let's just simplify that. Right, 0 equals 50 plus 120 VC. And if we rearrange that slightly, we're going to say it's got 120 VC, so I've just left that there, and I'm subtracting the 50 to the other side, so it's minus 50 on the right. And that's good now, because now we've got a minus, which suggests that this is going to recoil and come backwards. If we divide by 120, we get VC equals negative 50 over 120, which is, I don't know exactly, but it's a negative, that's the important thing, and it's less than a half, so I think it's going to be around 0.42 meters per second, 0.42, 0.43. Anyway, it doesn't really matter. Right, so it's negative 0.42 meters per second. So that's the crucial bit. We get this negative. So it is going to move in that direction. So it is recoiling. And we've used the maths and the physics to actually prove that it's recoiling. But also, if you notice, it's a really, really small velocity. This was 50 meters per second, but that's tiny. So that's a good thing. So you fire a cannonball out. Let's say you're in Dartmouth Castle and you've got those cannons, or Brixham, up at Berry Hedge, you've got those cannons, you're firing them out. You don't want the cannons themselves to start recoiling and move really, really quickly back. But you do want the balls to move faster. The thing is, so if that number increases, you've got a greater momentum to the right, which means the cannon itself is going to have to recoil at a greater speed. So, I mean, that's just something which you have to accept. Or you can make the cannon itself much, much heavier. If it's much, much heavier, it's not going to recoil as much. But if you think about on like pirate ships, I don't know if you've ever watched any documentaries or films where they show cannons on pirate ships and whatnot, they fire a cannonball out of the side of a ship, and the whole cannon itself recoils quite violently. I mean, that's about half a meter per second. That's about that sort of distance. 120 kilogram object moving that sort of distance in the space of 1 second. I mean, it's going to decelerate, but what if you're stood behind it? What if you were to light this little cannon, right? You set fire to it, excuse my drawing. Flames do not go off to the left, they always go up. Anyway. You light it, you're stood behind, you just don't think twice. You light it, the cannon flies out that end, while the cannon the cannonball goes out that way, you're just going to be struck by this 120 kilogram object. So you've got to factor these things in. But explosions occur in other scenarios as well. So if you had a gun, a gun and a bullet might weigh 1 gram, 2 grams. A gun itself maybe 200 grams. I don't know. I'm making these values up, but the point is you can do the same questions using different numbers. And you can find out how fast a gun would recoil. But anyway, that's enough from me. So you've watched the videos, you know what momentum is, conservation momentum. What I'd like you to do is try some of the questions that I post on Google Classroom. Give them a go. If you have any questions, if you struggle with them, send me a message or send me an email on Google Classroom or something like that. And if you want to check your answers, then let me know and I can send you the solutions. All right, hopefully see you next week and speak to you soon.